Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. This podcast will discuss another root-finding method called the secant method. As all root-finding methods are, they are used to approximate roots of nonlinear equations, just like bisection and Newton's method. It uses the idea of the slope of the function but without requiring any analytical derivative of the function. So it will use a numerical slope of the function, the slope of a secant line. The function must be continuous, but it doesn't have to be differentiable. For Newton's method, we needed the function to be differentiable because that involved taking the derivative. But for secant method, we don't need to know the derivative. So what's the main concept, the main idea of how this all works? Well, we write the equation as f of x equals 0, just like for the other root-finding methods. We find an interval from x0 to x1 in which the desired root lies. So we have a function here, the blue curve, where the function is negative at the left end, it's positive at the right end, and so there must be a root in the middle. So we find that interval, in this case between 1 and 2. We approximate the curve using the secant line connecting x0 f of x0 and x1 f of x1, as opposed to Newton's method where we would take, say, one of the endpoints and draw a tangent line. Now we take the 2 points, one on each side of the root, and we draw the secant line. We compute where the secant line crosses the x-axis, or let y equal 0. So we get this point over here where the secant line crosses the x-axis. And this is our next iterate. And we repeat until the answer stops changing. We keep the last two values, x1 and x2, then x2 and x3, and so forth. And finally, at the end, we make sure that the answer makes sense, that the y value is close to 0. So it's just like Newton's method, except we're using a secant line instead of the tangent line. Here are the details. We write the equation of the secant line through the 2 points. Y minus the y value, here we're using the right point. Y minus the y value is equal to the slope of the secant line times x minus the x value. And we define x2 to be that value of x such that the y value will equal 0 at that point for the secant line. So we just plug y equals 0, we plug x equal x2, and we solve for x2, and we get something that looks a lot like Newton's method, not surprisingly, that the new value should equal the old value minus the function value at the old point divided by a slope. Right? This is just like dividing by the slope, whereas in Newton's method we had f of x over f prime of x, xn. Here we have f of xn divided by the slope of the secant line. We'll work the same example, approximate the cube root of 2. So we find an equation for which this is the answer, x cubed minus 2, right? X cubed minus 2 equals 0. We consider finding a reasonable starting guess. We note that f of 1 is negative. We know that the cube root of 2 is between 1 and 2. So we take a look. F of 1 is negative 1. F of 2 is 6. Since f is continuous, there's at least one solution on 1, 2. We'll let x0 equal 1 and x1 equal 2. But that's really arbitrary. We could just as well let x0 equal 2 and x1 equal 1. So it really doesn't matter which point we call x1, which one we call x0. We perform the calculation. Here we have the formula up here. We only need the function value. We started with the x values equal 1 and 2. The y values were negative 1 and 6. We plug those values into this formula, and we find the new x value, 1.14. So, and we move everything over. We move x equal 2. It now is our 0th point, and x equal 1.1426 is the other point. We find the y value at 1.14286, and then we perform the calculation again, and we find our new value of x. And what we do is we take the previous value and the new value, and those are always going to be our values that we're going to use at the current time. So each time the new value moves over to this column, we see 1.25971 moves over to the second column. Right, the previous value that was in the xn column moves to the xn minus 1 column, and we find f of x values, and we find the new value. Notice that at each time interval, we only need to find one new function value because the function values just move right over. So it's very simple. Only one function value is needed at each step, and we note that the number that we have at the fourth step, 1.25992, is correct to all the decimal places shown. So the method converges pretty nicely in many cases. Okay, graphically, what happened? We started with x0 equal 1, x1 equal 2. We drew the secant line. We saw where the secant line crossed the x-axis, and that was our new value. Then we'd go and take the new point over here, the y value at 1.14286, and we draw the tangent line again, and just go on in that manner. What are the properties of secant method? Well, there's only one function evaluation required for each step. There are problems if the slope of the secant line is near 0, just like if the derivative is near 0 for Newton's method. The iterates may migrate far from the desired root if that slope of the secant line is near 0. The current pair of iterates may not bracket the root in this case. We're just taking the last two iterates, and if they're both on one side of the root, that's okay, and we're just going to keep going with it. And it does not require knowing or computing a derivative. The error analysis is similar to Newton's method, but it's somewhat more complicated. We'll just give you the results and what it implies. It can be shown that if alpha is the exact root, that the error at the n plus first step is equal to some function, a Taylor series looking thing. It's just like what we had for Newton's method, times the error at the nth step times the error at the n minus first step. For Newton's method, we had the error at the nth step squared. Here we're depending on two previous iterates. So what we find is that the error at the new step is proportional to the error at of the previous step times the error at the step before that. We can get the basic idea, the behavior of the error, if we let this messy piece equal 1. It turns out that one can do some analysis and show that it's not important that we're making this assumption, but if we let the error at the n plus first step be the error at the nth step to some power r, we're going to figure out the order of convergence. And so if we plug that in over here, e to the r, that en to the r is the error at the n plus first step, then what we get is error at the n plus first step is the error at the nth step to the rth power is equal to the error at the nth step, and the error at the n minus first step would be the error at the nth step to the 1 over r. Since the bases are all the same, we can put things together, and we find that r, the order of convergence, must satisfy the equation r equals 1 plus 1 over r, which is the same as this quadratic. We solve the quadratic, and we get the golden ratio as the answer. The negative value of r really doesn't make sense in our case, and so what we find is that the error at the n plus first step is approximately the error at the nth step raised to the 1.618 power. Newton's method, that power was 2. Bisection, the power is 1. Order of convergence of bisection is 1. Order of convergence of Newton's method is 2. Order of convergence of the secant method is 1.618. There's another method that's very similar to secant method that's called regular falsy. Regular falsy, it's the same as the secant method, but we force ourselves to bracket the root at each step, just like with bisection. So we're kind of combining pieces of secant method with bisection. By bracketing the root, we guarantee that the method will converge, so it is more robust, but it often slows down the convergence. And here's the table that we had earlier for the secant method, and for regular falsy, we show what happens. In this case, the y values are negative and positive, and then at the next step they're negative and positive, but after that they're both negative in the secant method. What happens in regular falsi is when that occurs, that we're going to bracket the root. We're not going to keep the most recent of the previous values. Instead, we're going to take the value x is equal to 2 because the y values always fall below the axis at our new x value. So the first step we get the same new x value. The second step we get the same new x value. But at the third step we're still keeping x equal 2 and y equals 6, which forces the new x value to be 1.23884, which is different from earlier. And for this particular case, and in many cases with regular falsi, you'll get that one of the iterates will pretty much be constant. At least after a few steps you'll be using that same iterate. We notice, or we remind everybody, that for secant method the value here at the fourth step was right to all the digits shown, and we see that we have 3 digits that are not correct with the same number of steps with regular falsi. So it is slower, but it does guarantee convergence. A moment of culture. Once there was a surgeon, an architect, and a computer scientist who were on their way out for a drink after work together. On their way to the bar, they were accosted by a lady of the evening. However, all 3 men were happily married, and so they tastefully declined her offers and moved on. Naturally, she was mentioned in the conversation, and somehow the topic got around to the world's oldest profession. The surgeon began and said, "Well, I think it's not really true. I mean, look at it. Right there in the beginning of the Bible, it says God reached into Adam and pulled out a rib and fashioned Eve. If that's not surgery and biology, what is? It's obvious surgery really is the world's oldest profession." The architect responded, "I'm not so sure about that. Look, even earlier in the Bible, it says God took the chaos and the void and created the earth and its contents. That's clearly architecture. So it follows that architecture is really the world's oldest profession." The computer scientist thought for a moment and said, "Hey, but where do you think the chaos came from?" I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.